Alrighty, good morning, my chemistry students. Today we are introducing officially Unit 2. We're starting with a little bit of a review from some concepts that hopefully you might remember from physical science, and then we're going to get into explicitly learning about intramolecular forces, which deals with standard SC2A and SC2C. Starting with what hopefully you remember from physical science. So Unit 1 was all about introducing atoms, atomic structure, and how the atoms put together. But now we're going to think even bigger than atoms, and we're going to start thinking in terms of matter. So matter is anything that has mass and takes up space. For example, the air in the room is matter. It takes up the space, it has a mass, therefore it is matter. The light in the room, though it takes up the space, it fills up the space, light does not have a mass, therefore it is not matter. Now matter can be classified by several characteristics. We can use their general physical properties to classify matter as either a pure substance, element, compound, mixture, which can be further classified into homogeneous or heterogeneous mixture. These are the classifications of matter. We also have states of matter, which is our solid, liquids, and gases. So talking a little bit about the classification of matter is if the composition of the matter is fixed. Basically, if it's always the same no matter where I get it from, that matter is an example of a pure substance. But if the composition of the material varies, then the matter is a mixture. It's kind of simple, easy to remember terms. If it constantly changes, it's a mixture. If it has a set ratio of stuff, then it is a pure substance. So pure substances can be further classified as elements or compounds. So elements are pretty easy. Elements are the things that are on the periodic table. They're what we were learning about in Unit 1. Elements are the simplest form of matter. They have a very unique set of chemical and physical properties that is relevant to only that element. Elements, of course, cannot be broken down into simpler substances. They can only be broken down into subatomic particles. Examples of elements include nitrogen, oxygen, sodium. Basically, anything that's on our periodic tables is considered an element. Now, if we take two or more elements and we combine them together and we form a bond between those elements, that is called a compound. A compound contains two or more elements that are in a fixed proportion. So the ratio of the atoms is always the same for compounds. Doesn't matter where I get the compound from. Now, it is interesting to note that compounds can be separated into elements. That typically requires a chemical process, but compounds can be broken down where elements cannot. Some examples of compounds include water, sugar, vegetable, well, that's technically mixture, oil, or do general term, oil, not vegetable oil. So mixtures is when you have a blend of two or more components. Mixtures occur when the compositions are not set. So mixtures can be further classified as heterogeneous or homogeneous. And what you see in the mixture basically determines its classification. So heterogeneous means that it is a mixture that does not have a uniform composition. Your eyes can visibly see different colors or shapes or textures in that mixture in order for it to be heterogeneous. It is made up of different parts. Some examples of mixtures include salad, pizza, beach sand. A lot of the food that we eat would be examples of heterogeneous mixtures, but I can visibly see the different things that make it up. Comparatively, you have homogeneous mixture. Homogeneous means that it looks the same throughout. So the composition is uniform, and I cannot visibly see what is actually making up that homogeneous mixture. So for example, if I had a flat or an unopened bottle of soda, that would be a homogeneous mixture. I'm picturing in my head a Coke that's just brown, or a Sprite that's just clear. I can't see the acids and the sugar and the water and all the food coloring and whatnot that makes it up. Can't identify them. It just looks like either a clear liquid or a brown liquid. Tap water. Your tap water is not a compound because tap water contains impurities, especially if you're in Henry County, you're on the county water or city water. You've got chlorine and fluoride. There we go. That was the other thing that's in your tap water, as well as who knows what else might be floating around. Those are examples of homogeneous mixtures because tap water tastes different depending on where you get it. It looks different sometimes. It is interesting to note that homogeneous mixtures, if it happens to be a liquid, a homogeneous mixture that is a liquid is called a solution. We will talk a lot more about solutions later in the course, but a solution is simply where you have a solute dissolved in a solvent. So the solvent is the thing being dissolved. The solute is the thing doing the dissolving. My example here is Kool-Aid. So my solvent would be water because water is needed to make Kool-Aid. It's the thing that does all the dissolving. My solutes are the little things that I put in the water, the sugar, the Kool-Aid powder for making lemonade, the lemon juice, whatever goes into the water are my solutes. Now we do have some solutions that are alloys. You have to heat them up to actually get them to turn into a liquid, but an alloy, a mixture of metals, is also considered a homogeneous mixture because you can't visibly identify the different metals that make it up, but it's not just one metal. So, trying to classify a sample, you've got a little flow chart that you can kind of think your way through as you're looking at your sample and you're trying to determine what is its classification. So first thing you're going to ask yourself is it uniform? Because if I can visually see different things in it, then it has to be a heterogeneous mixture. So if it is not uniform, it has to be heterogeneous. If it is uniform, then I'm going to ask myself, well, can I separate it? So like if I've got a saltwater solution, I can boil off the water and get the salt. It looks the same, looks like a clear liquid for the most part, but because I can physically separate it, it would be an example of a homogeneous mixture. If I cannot physically separate it, then it's going to be a pure substance. So then you have to ask yourself, well, can it be broken down into something else? So if it's not on the periodic table, it's not an element. So it's probably a compound if you don't explicitly see it on the periodic table, and it's something that you know is not a mixture, and it looks the same throughout. So nice kind of flow chart to organize your thinking as you're trying to classify matter. So take a moment and see if you can identify what these substances would be classified as. So butter, I'm picturing in my head the butter in a big old tub that's in my refrigerator. So is it uniform throughout? Well, yeah, it's all one color. It's kind of a yellowish, orangish color. Is it made of, can it be physically separated? Technically, yes, it can. Butter, as with many foods, has an ingredients label, and I can look on that ingredients label and see that there are tons of different things that make up that butter. Therefore, butter must be a homogeneous mixture. All right, xenon. Picture those nice, pretty glowing lights. Technically, those are neon, but close enough. So xenon, does it have uniform composition? Yes, so it's not heterogeneous. Can it be separated? No. So it's got to be a pure compound. Or can it be separated physically? No. So it's got to be a pure compound. Is it on the periodic table? Yeah. Xenon's an element. It is on the periodic table, therefore it is an element. Salad. Salad. I picture salad in my head. Doesn't matter what kind of salad you picture. It's going to have different parts. Therefore, it must be a heterogeneous mixture. It does not look uniform throughout. Epsom salt. Epsom salt, you may have seen this to help soak sore muscles. It's also laxative. But Epsom salt is just a white crystal. Well, it's uniform, so it's not a heterogeneous mixture. We look at this Epsom salt, the ingredients labels, it can't be separated physically by any means. And in fact, if we notice, it is actually called magnesium sulfate. Epsom salt, also known as magnesium sulfate, is a compound. It's a compound that happens to contain 3 different elements. So pool water. Think about the things that go into your swimming pool or a swimming pool. Hopefully they do look uniform throughout, but we can take that pool water and we can physically separate it. If you've ever been around a pool long enough, you can see the water evaporate and you're left with chlorine, or if you have a saltwater pool, salt on the side of the pool. So therefore my pool water must be homogeneous. Uranium, well, it's on the periodic table. If it's on the periodic table, it's got to be an element. So chocolate milk, does it visually look the same? Yes. So it's not heterogeneous. Can I separate it physically? Not very easily, but yes, you could separate the chocolate from the milk. Therefore, it must be a homogeneous mixture. So now that we've talked about the classification of matter, it is important to note that that term, classification of matter, applies to our pure substances, our elements, compounds, homogeneous mixtures, and heterogeneous mixtures. That is the classification of matter. Now, matter not only can be classified based on its properties, but it can also be organized based on the state that it is in. So, state of matter or phase of matter. I use these terms interchangeably. But there are 3 states of matter that we encounter on a regular basis here on Earth: solids, liquids, and gases. There is a 4th state of matter, plasma. It's just something we don't get to really play with too terribly much here on Earth. So our first state of matter is a solid. Solid is a substance that has a definite shape, definite volume. The atoms are in a fixed position. Therefore, the substance will not take the shape of their container. I can put my calculator in a pot and it's going to stay calculator shaped. All of these atoms, if I were to kind of draw what it looked like, they are all right next to each other. Yes, the atoms are moving. They're just vibrating very, very slightly in a very small amount. But solids, their shapes don't change. Their volumes don't change. Solids cannot be compressed. A true solid cannot be compressed. Now, the interesting thing to note about solids is they tend to have the least amount of energy of any state of matter. So if I get substances cold enough, they will all turn into solids. My second state of matter is a liquid. So liquids, think pouring. And if you think about pouring, you know that liquids have a set volume, but not a set shape. So I can take a cup of water and pour it into a bowl. It's going to go from a column to a bowl shape. I take it from that bowl and pour it on a plate. Well, it's now plate shape. I pour it on the floor and it's now floor shape. It's flat. It's going to spread out and take up, or not spread out, but it's going to change its shape, but the total volume of the liquid that is there is constant. If I was able to gather up all that liquid from the floor and put it back into the original cup, I should have the same original volume. So liquids do not have a set shape, but they do have a set volume. They take the shape of their container. So if I was trying to draw a container with a liquid in it, the atoms are still going to be fairly closely packed. They're going to be close to each other, not a lot of space, maybe a little bit of space, but they're going to fill up the bottom of the container. And whatever shape that container is, that's the shape they're going to take. Now, liquids, because the particles are not in a fixed position, they're able to slide past each other. That's what gives liquids their property to flow. That's what makes them viscous. Now, liquids are slightly compressible, very, very, very slightly compressible. In fact, their lack of shape and their minimal compressibility is what makes many liquids really good for hydraulics. It allows you to lift heavy things by just pushing on liquids. Now, liquids have a little bit more energy than solids. So in order to go from a solid to a liquid, I would have to add energy. To go from a liquid to a solid, I'd have to lose energy. Third state of matter, this is the last state of matter that we really get to play with here on Earth, and that is a gas. A gas, those atoms are not in a fixed position. They occupy the entire space of the container. They spread out and change their volume. So if I was trying to draw an illustration of a gas, I would have my container with the atoms all spread out. They don't really touch each other. Gases, there's very minimal attraction between those atoms. They have a lot of energy, and because they have a lot of energy, their atoms are able to kind of zoom around the container and move in random directions. Now, gases, because the atoms are spread out, also are very, very highly compressible. I can take a gas and smush it down into a considerably smaller volume. Don't know how many of y'all have encountered this, but I have at my desk a can of air. And if I were to shake this, it sounds like a liquid. And the reason it sounds like a liquid is because the gas that's in here, you can't really see it. Wait, hold on. There we go. The gas that's in here has been compressed so much that it has been turned into a liquid. And that's something that under immense pressure we're actually able to do. But gases change their volume, they change their shape. Gases have the most space between them. They also have the most energy. I think I already said that, but whatever. So, fourth phase of matter. The fourth phase of matter is plasma. And you got to be careful because in chemistry, we do not mean the plasma in your blood. We do not mean the plasma in your TV. We mean the state of matter. And the state of matter of plasma is a gas that has been ionized. So basically, it's got no electrons. All of the electrons have been yanked off. It has gotten so much energy that the electrons have went, whoop, I'm gone. And that is how we get our plasma. So on Earth, plasma really only exists for very short amounts of times. You see it anytime you see a lightning bolt. But the most closest continuous sort of plasma to the Earth is the sun. So in the sun, you've got hydrogen, helium, other gases, and all of those gases are just the nuclei. There are no electrons in that sun. They've been yanked off of the plasma. If I wanted to draw plasma, it basically looks exactly like a gas, except for it's got a positive charge because it doesn't have any electrons. But not likely to ask you to draw your plasma. We are going to focus more on just our three states of matter. So see my nice, lovely illustrations here. Does relate their energy to each state of matter and how we can describe their shape and volume.